Hello and welcome to another video, this time on the Mat 2013 question 4. This one quite nice. I'm not going to spend too long on this one because I think it really is mostly very nice. Certainly it starts off with sketching a rational function. That shouldn't stress you out. This is the way I see rational functions. Firstly, any division by zero, you're always going to get a vertical asymptote. Any division by zero always gives you a vertical asymptote. And so we're going to have a vertical asymptote at x equals a, because that's where we'd be dividing by zero. Secondly, behavior at infinity. When x is really large, you basically got a million plus a over a minus a million. Now make a small for this to make sense. Let's say a was 1. 1 plus a million over 1 minus a million. Oh, what's that going to be? Well, basically it's going to be 1 but negative, yeah, because it's going to be a number slightly bigger than a million over a number, very negative but very close to a million. And that means that we're definitely going to be heading towards y equals minus 1. Yeah, when x gets super large. Yeah, because remember, you might be thinking, well, why have you made a small? Well, we can make x arbitrarily large. Yeah, whatever a is fixed at, even if a is like 1,000, we can still make x like 1,000,000,000, because that's what we're doing when we're heading in that direction. Yeah, so we can see the behavior at infinity. And so that's what tells me it's actually going to be, and now you might think, oh, which side of the line is it going to be? It's going to be underneath it here, because if you look at my example there, it gives you, roughly speaking, a number slightly like say, I don't know, minus 1.000001. But the point is, it's going to be in this side of the minus 1, not on that side, not above it. And it's the same here. We know that we've got an asymptote here, so it's going to curve down there. And you can check if you like, pick a number slightly bigger than a for x, like I don't know, we could have it as like a plus a tiny bit, yeah. Well, a tiny bit isn't going to matter, and you're just going to have 2a on the top, but the tiny bit is going to matter on the bottom, because you're going to be doing a minus a, and you're going to be left with like a tiny bit, but negative. And that's why when you do the number which is fixed here, like whatever it is, 2a divided by a tiny little number but negative, it's going to be very negative, and it's going to be down there as well. Now we also want to know, when x is 0, what is y? Y is a. When y is 0, what is x? X is minus a. And so it's going to look something like that, yeah. Oh, but there's one more thing. I almost forgot. We're only going in that range. I'm really showing you how to sketch the whole thing there. That is supposed to be going up to the asymptote up there and down to the asymptote down here. But yeah, what we've actually shown, we only need to do it from minus a up to a. So let's do that. Oh, sorry. And that's a on the y, so I should be pointing that out here. So all I really needed for my graph was doop. There's the y, there's the x. We're only drawing up to there, which is where x is a. That's an asymptote, and it starts off at minus a. And hopefully you can see it's increasing. And so that was part 1. Okay, part 2. Part 2, easiest bit of the question, really, I think, part 2. Because if we think of this as y and x, maybe I've just seen this kind of question before, but that's where my y and x coordinate axes are going to be fixed at the origin there. Then we can use, everything they've told us in the question. We can use this. Oh, well, the x coordinate is sine theta. Sorry, I can't read. Sine theta. So I'm going to square that. That's sine squared theta. 1 minus sine squared theta is cos squared theta. Y squared, let me write this down. Y squared is therefore going to be 1 minus sine squared theta, but that's cos squared theta, and so y is cos theta. Strictly speaking, plus or minus, but I can see y's got a positive coordinate there, so I'm going to call that sine theta cos theta. I'm going to do exactly the same trick over here. I'm going to have minus cos theta. I'm going to square it, giving me cos squared theta. Then I'm going to be doing y squared is 1 minus cos squared this time. That's sine squared, and when you square it, you're going to get sine, and you know it's positive because it's above the axes again. Next thing I noticed, and I know this is very quick because you want to look for this, doesn't that look like a right angle? Well, that's because it is a right angle. Yeah, and that's why, in order to establish it, to prove yourself it, just think of the gradient of this line. That gradient is cos over sine. Look at the point. This gradient is sine over minus cos, and they are negative reciprocals, and therefore that is a right angle in the middle there. That's great because we can easily work out the area of the sector. The sector area is going to be a half r squared theta, where theta is pi over 2. This is going to be easy to work out the area of, as is that, because you've just got like, that's cos theta and this is sine theta. So let's actually write it down. I think we can write down the area of A now. A is just going to be equal to a half r squared theta plus cos theta times sine theta times a half, and then cos theta times sine theta times a half. And all of that simplifies to, well, we'll plug in r as 1, we'll plug in theta as pi over 2. We're going to get pi over 4 plus sine theta cos theta. Cool. Done. Okay, part 3. This was the most annoying bit. I came up with a lovely solution which didn't follow their instructions. There's a really obvious solution actually. The sine theta cos theta. There's a reason why they said only, yeah, because the easiest way to prove that surely is with double angle formula. If you've done double angle formula, you know that sine 2 theta is 2 sine theta cos theta. Well, in that case, a half sine 2 theta is sine theta cos theta. And now you can just see it. All I need now is a sentence just saying, well, clearly sine 2 theta is trapped between 1 and minus 1. And so a half sine 2 theta will be trapped between a half and minus a half. So in fact, I can go a little bit further than that and say, well, a strict inequality I can see here, is actually missing something in some ways. We can actually say that's true if we use this result, so we get a little bit more out of it. Now, they don't want you to use that. That's why they're saying only use sine squared plus cos squared is 1. That's really mean of them, because there's lots of ways you can prove it, actually, loads and loads and loads. Now, if you're only using sine squared plus cos squared is 1, that's a bit harder, though. It really is. It's not necessarily that obvious. I suppose, you might think at first, well, if I have sine theta plus cos theta and I square it, I get sine squared plus cos squared, which is 1, plus 2 sine theta. Yeah, that's sine theta cos theta. Sorry. So I never give myself enough space on this board, do I? I'm doing long kind of mathematics and I'm not got enough space. Okay, so sine theta plus cos theta all squared is going to give you a sine squared plus a cos squared plus a 2 sine cos. That's certainly well worth bearing in mind, isn't it? Because that's actually 1 plus 2 sine theta. So what we can say here is that this equals 1 plus 2 sine theta cos theta. That was my initial thought on this. And then, yeah, I mean, if you had sine theta minus cos theta and you square that, that's going to give you something very, very similar, but it's going to be 1 minus 2 sine theta cos theta. Now, we don't, you might be tempted to add here, but that's not going to help you because we need the sine theta cos theta still in play. If we subtract these two equations, we end up with quite an interesting result because we end up with sine theta plus cos theta all squared minus sine theta minus cos theta all squared equals, the 1 minus 1 is going to cancel, but the 2 theta minus 2, the second terms are going to double, essentially, giving you 4 sine theta cos theta. Okay, that's kind of interesting, isn't it? That's kind of interesting. The ones have cancelled and we got left with this. Now, after you expand these brackets, you're going to have a sine squared plus a cos squared. Essentially, you're going to get the 4 sine theta cos theta. But this might give you an inkling of what we should be doing, because if we've got something like this, how are we going to get back down to sine theta? Well, can't we just replace some of these things in some way? Can't we just say, well, okay, hang on a second. Maybe if we did this a little bit differently, we could end up with a slightly nicer result. Let's try a little bit different. Well, if I expand this, I've got 1, because I've got sine squared plus cos squared, and then plus 2 sine theta, cos theta. And then I've got minus this sine theta minus cos theta all squared equals 4 sine theta cos theta. And then if I take that away from that and then halve it, I get 1 minus sine theta minus cos theta squared over 2 equals sine theta cos theta. I hope you can see I've done a couple of steps there. But the reason why I've done that is, can you see now? Sine theta cos theta can be written as a half minus stuff squared. And stuff squared is always 0 or bigger. And so this is enough to conclude, hence, sine theta cos theta is less than or equal to a half. But that's hard to spot. It really is. It's a tricky one, that one. It's really hard to spot. But there we go. I prefer being allowed to do it the really easy way. But there we go. Okay, part 4's not bad either. Because part 4, it says, what's the largest ratio of the area of A to the area of B? Now, let's work out the area of B first, because we already know the area of A. And the area of B is going to be, well, the area of a semicircle, which is pi r squared, which is pi times 1 squared. Oh, but then we've got to divide by 2. So that's just going to be pi over 2 minus the area of A. Yeah? Now, that's going to give me pi over 2 minus, I think it was pi over 4 minus sine theta cos theta. So in other words, we're going to get, after you've applied the negative, sine theta cos theta plus pi over 2. So let's have a look at what we got. If we're working out that ratio, we've got the area of A, which is pi. Oh, hang on, I've done. Can you see I've made a little mistake there? I know you'll spot it. Good for you as well. I like that. Like, because I don't spot everything at all. Okay, so what have we got for our area of A over area of B? We've got something quite nice. We've got something very much related to part 1. You're wondering when part 1's going to make an appearance again. Well, of course it makes an appearance. We've got A minus x over A plus x. Yeah, link it to previous parts of the question. They always want you to do that. There's a reason. If it looks, if you're thinking, oh, that reminds me of something I did earlier, look it up. It's bound to be the way to do it. Now, we now know, remember, that we're trying to find the largest ratio, which means we want to make the top as big as possible and the bottom as small as possible. Oh, have I got this written the wrong way around as well? A was pi of, look at this. That will teach me for not looking carefully at what A is. A is that, and B therefore is going to be the negative, because we're going to have therefore pi over 4 minus sine theta cos theta. I was going to say, it was about, my argument was a break down there, and that's why I knew I'd done something wrong. Because if I want to maximize the top, I need to make the top as large as possible. And I've already discovered that the largest value that can take is a half. And so if I want to maximize this, I also want to minimize the size of the bottom as well. And that means I want to maximize how much I'm taking away. So it works both directions. So we've got pi over 4 plus a half over pi over 4 minus a half. Tidy that up a bit, times everything by 4, you get pi plus 2 over pi minus 2. So yeah, nice question. Unusually nice at the end rather than nasty at the end. I thought the worst bit was part 3, but the rest of it, very, very nice question. Hope you enjoyed it. I hope you also found it a nice question, actually. But yeah, I'll try and get the last one of this paper loaded up as soon as I can. Okay, keep up the hard work, and yeah, also try and do that playlist for Alfie. Thanks for pointing out my mistake, Alfie. I really appreciate that. That was a terrible one as well. Really made me hang my head in shame. Well spotted. Okay, brilliant. Keep up the hard work, everyone, and bye-bye.